Hello again. Let's do video number 10, which is a continuation of our projectile motion, and let's do a more complex question. And in this case we're looking at a variation on something we did in physical science, which is now in physics, and that is where we launch something at an angle to the horizontal and it doesn't have to land at the same horizontal height. And so it's a bit more complicated. What is the more complicated part about it? Well, the more complicated part about it is, if you looked at it, it's the same as the vertical motion is like this, okay, where you go up and then come down. The horizontal motion is still constant velocity, and we've done that, and we should have an understanding about this. And we've done these types of questions, I think, in physical science. And they're a little bit tricky, but there's a variety of ways of handling them. Things that you can do is you can just look at the time it goes up, okay. Then if you want to, you can look at, let's change the color again, let's go, you can then just look at this section falling, okay, recognizing that it's actually falling a greater distance. So you have your 60 meters plus, so you actually have to work out that extra height there. And if you're really keen, you can work it out. Let's do it like this. You can work it out all in one go. So there's a variety of ways of looking at these questions. And so it's up to you to find which way you're most comfortable working out, what way your head works with it. Generally speaking, I teach a way of dividing it into sections and then recombining it, because that's the way my brain works. But once you get your head around that, you then might want to try and use one of the more complicated ways of doing it. So let's just look at a typical question. So here we have the angle. It's getting launched at 88.3. You're 60 meters above, and that's all you're told, but you're asked the usual sorts of things: how far, how long in the air, how far from the cliff, etc. What's the impact velocity, all those sorts of standard things. Alright, and so first thing that we would do is you would work out your horizontal and vertical components. Where's my pen? There it is. And that's what they've done for us here. Let's just make this a little bit thinner. So there's that one, and there's that one. So we should be moderately proficient at that. And then I would always list down our vertical U, V, A, S, and T. Alright, and it takes a little while. And U, V, that's a U, A, S and T, but it's good practice to get into. And let's assign all these numbers, shall we? So what do we got? In terms of the vertical, we've got the initial vertical velocity is plus 50 meters per second to the minus 1. What else? We have the initial horizontal velocity, which I think is 72.8 meters per second to the minus 1, and so this is going to be 72.8 meters per second to the minus 1, and A is going to be 0. What else we know? We know the final vertical displacement is going to be minus 60 meters, which is important, that minus. The acceleration, now they're going to use minus 10, but if we were to do it, we'd use minus 98.81 meters per second to the minus 2. And we don't know the time, and we don't know the final velocity, but we've got our three things, so that makes us happy. Okay, alright, and we could work it out in a variety of ways. We can just look at how high it goes up. So if we did that, we would say that V equals 0. We could work out the distance it goes up, so we could get rid of this S, and instead of using minus 60, we could work out how high that goes up, and then we could go how far it's going, 60 plus x is how far it's going to fall. We make that minus. There's a whole lot of different ways of doing this sort of question. So let's just go through one way that the textbook does, and when you start doing some questions you might have a go at doing it different ways, depending on the question. So they've got all this sort of stuff, and the first thing is working out the time that the ball is in the air. So they put it straight into s equals ut plus half at squared. Now the problem with this is if you get to this stage here, you recognize that this is a quadratic equation, and solving a quadratic equation is quite difficult, and most students make mistakes. And so what I would recommend is, if you come to this situation, and the situation is difficult because we don't have a v, and if we know these three things and we're trying to find t, so if we know u, a, s, and we're trying to find t, it's very tempting to use this equation, but you'll hit a brick wall. And so what I recommend is you find v first, find your unknown v by using v squared equals u squared plus 2as, and then solve for t. Now you can work it out you can work out just the section going up and then the section going down, or you can work on the whole equation. As long as you know what you're working out in terms of the time, and you come to the final conclusion, and that time is the total time, you can then work out everything else. Alright? And so that's the way I would recommend that you work it out. So have a think about that. Right? Then, once you've done that, everything else is really easy. The impact velocity is, well, you've got the horizontal component, you then just have to work out this vertical component, and by putting it into v equals u plus at, and working it all out, because you've just worked out the time, which is 11 seconds, you can then combine your two components, get your resultant by using Pythagoras, which is 95 meters per second. Then you find the angle here, which is the angle down from the horizontal, and then, because we're a model student, we would write our answer as 95 meters per second minus 1 at 40 degrees down from the horizontal. That's why I don't write too often. Okay, and that tells us, if that's the horizontal, we go down 40 degrees, and that will be our velocity. That's a terrible 40. Alright, got that? Okay, let's carry on. And then just working out the horizontal distance, they've just used v equals s on t, rearranged, so s equals vt, and they get that answer there. Now, in a textbook that you have on your OneNote, and you can borrow from the library, they have a thing called a range formula, and that is a really bad thing, because it's evil, because this range formula only works in situations like that, where it lands on the same horizontal. Okay, it doesn't work on situations like that, where you're after that distance there. Okay, so I generally find no benefit whatsoever in that formula. Even for these types of questions, it's not that hard to work out how far it travels. Okay, because you just do work out all the parameters you need to know, and away you go. You end up with a better understanding of the question. Alright, so don't use that range formula. Now, some things you may be asked about is, we never really have to calculate the effect of air resistance, but you need to know about it quantitatively. So you might be asked, what would be the effect if we took air into consideration, or air resistance? And so the red dashed line here represents the perfect parabola that you get if there's no air resistance of a projectile motion, whereas if there is air resistance, remember the force of air resistance is always in the opposite direction to the velocity, so it changes direction, and it is proportional to the actual velocity. And so if you've ever seen a golf ball being shot, you might think, well, how do they get it just to land on the green and just go plop? And it's because the projectile motion is no longer a parabola, it's much steeper on the second half of the flight, and so it doesn't hit the ground with as greater angle. And it's one of the reasons they put dimples on the golf ball, because as it spins and as it moves at certain velocities, the air resistance changes, and so in this section here it becomes very steep and will just drop and bounce. Whereas when you use something like a driver on a golf course, not that most of you are interested in golf, you get a much more parabola shape, and so the ball bounces further along. There's a whole lot of science in sport. That's why they have a subject called sports science, but unfortunately that subject doesn't do much science. If you're going to study science in sports, you're better off doing a science and learning it all and then applying it. But that's just my personal opinion. Okay, but you might be asked, for example, what would be the effect of air resistance on this projectile? And obviously the range is less, time of flight is less, and things like that. Okay? Now, there's a whole lot of real-world applications to projectile motion. Here's some welding arcs, firing things at other things, and bouncing balls and things. And so there's a whole lot of animations available on your OneNote, where you can fire a cannon at a target and do various other things. And so just get your head around all the different types of projectile motion that are out there. Alright? And there's this neat little picture which multi-exposure showing a ping pong ball bouncing across the table. There you go. Now in the next video we're going to look at what we know about momentum, work and energy. Cheerio!